Okay, let's just see. So I have a couple transistors here, Mn1, which is 1 by 40, and then let's just see, where is Mn3, another MOS, 1 by 0.7. This Mn5 is 1 by 10, something like that. So, like this, see, we have something like this MOS diode configuration here. And then I have a similar thing in PMOS side. PMOS side, something like that. And then I will sweep this drain source voltage. Sweep this drain source voltage, okay? And then we'll plot current. And then find out, see, I will plot something like ID, VDS. Actually, this is the same as a VGS, right? So this is, if I plot log plot, say I will find my curve something like that. This is some current. Say, for example, let's just say 1 by 0.7 will be looks like that. This 1 by 40 will be very slow. Then this 100 nanoamp will be, where is my 100 nanoamp? 100 nanoamp, is it right? Yeah, something like that. So, oh yeah, you cannot see blue. Yeah, okay. Let's see. Yeah, this is 1 by 0.7. Say there may be another one. This is another 1 by 40. Okay. Then say assume this is my 100 nanoamp line. And see, but I hope it works at in strong inversion with a 1 by 0.7 and service threshold weak inversion for 1 by 40. Okay. So I want to find out which size transistor works in strong inversion and weak inversion at the drain current of 100 nanoamp. Okay. Okay, let's do that. Oh, let's see. Let's look at the MOS first. This is N1, N2, where is N3? Oh, this is N3. So I have I will plot semi-log here. This is a red one is 1 by 0.7. This is 1 by 10. And this yellow one is 1 by 40. Okay. So 100 nanoamp is here. So here, see, 1 by 40. Yeah, definitely in weak inversion, right? Red one. The center one, this one is, I think it just still works in weak inversion, right? So, this straight line is subthreshold. This one is this is square law. This is actually square law. Square law dependence is a strong inversion. In the middle, there are some intermediate. Weak inversion includes that part, okay? So this 1 by 10, yeah, I can say this is, it may be in subthreshold or weak inversion. But for this yellow one, 1 by 0.7, oh, sorry. Actually, this is 1 by 40. Is it right? Let's just see. Oh, yeah, sorry. Yeah, this is 1 by 0.7. Yeah, strong, weak inversion, right? Say, I can say 1 by 10 also works at the weak inversion. at the 100 nanoamp. Okay. For this one, so this yellow one, this is 1 by 40. So I can say 1 by 40 works in strong inversion. All right. So I will change all the transistors into 1 by 40 for strong inversion current source. Okay. PMOS about the same. PMOS. I did the same thing for the PMOS. Okay, with a similar sizing. Question? Okay, let's move then. So self-bias weak inversion, we redesigned those circuit. Let's see. We have a pretty, no, not very long. Okay. So let's see. Okay. How come? All right. This is pretty long. Oh, should be self-bias. Self-bias, right? Okay, so if you look at the net list of this self-bias circuit, is this weak inversion? Yeah, weak inversion. Say for this one, we put all NMOS transistors in 2 by 0.7. Actually, 1 by 0.7 got some slight problem, so it was shifted toward strong inversion. So all NMOS transistor changed to 2.7. There is 8 by 0.7. The resistance was reduced to 230K. Somehow it needed some adjustment. For the PMOS, all the size was changed to 6 by 0.7. Actually, one transistor. Yeah, we have a smaller transistor here also. Oh, okay. So this one, you may comment that capacitance stuff. So instead of say in a previous design we used 10.7, this one was changed to 2.7. Do we have a small transistor here? Oh yeah, this is a small transistor for that cascode biasing. PMOS was changed to, it used to be 20 by 0.7, right? It was changed to 6 by 0.7. It still works in a subthreshold at the 100 nanoamp. Okay? So I hope we use this bias circuit for your homework. Question?
그러면은 저항은 N부스 쪽에 닿는 거예요? P모스 쪽에?
Oh yeah, you can do it whatever you want. Okay. Okay, so yeah, this is for weak inversion current source. Those are tail current source of NMOS differential pair and PMOS differential pair, right? That's for that biasing. We need a strong inversion bias circuit, right? Yeah, so how can we make a strong inversion bias circuit? Let's look at the strong inversion bias circuit here. So let's look at the circuit part only, okay? Let's eliminate all others. Okay, this is a circuit part. Uh-oh. All right, this is my circuit part. How come this PS is here? It's a little bit large. Okay, fine. So, yeah, let's look at the strong inversion self-bias circuit. So what's the size of this one? NMOS was 1 by 10, right? Oh, there was 1 by 50. Oh, this is a very large one. Maybe you can say 1 by 40 or something like that. This is for cascode biasing. There is a 4 by 10 here. So NMOS is 1 by 10. How about PMOS? PMOS is where? Oh, 1 by 3. Is it right? 1 by 3. PMOS is 1 by 3. Yeah, there is, okay, there is 1 by 15 is a cascode biasing. We already checked, say, 1 by 10 NMOS works in strong inversion at the drain current of 100 nanoamp, okay? So, you know, in a surface threshold, I mean, strong inversion case, that, oops. Yeah, this is NG1, NG2. Yeah, we put some S here because this is a strong inversion. My diode will be connected like that. So here, see, you can find the current I. Current I will be, this is a W of L, this is a 4W of L, right? Current I will be 2 mu Cox W of L R square, something like that, okay? Then what's my GM? GM should be 1 over R. GM is what? GM equal 2 mu Cox W over L I, right? Say, then if you substitute this I there, then what? Oh yeah, this is just 1 over R, right? Okay? You can check. So GM biased by this current source is all proportional to 1 over R. See, I have, say, W over L2 is connected there. The GM of this one is only what? Hey, where is my GM? Yeah, GM of this transistor will be just W over L ratio over 2 over W over L times 1 over R, okay? So GM is proportional to 1 over R. This is for strong inversion. In the surface threshold, we could find a similar thing, right? So in a weak inversion thing, the GM is also proportional to 1 over R. Say, for example, something like that. Yeah, this is a weak inversion. Weak inversion, yeah, see, this is 4W over L. This is just a W over L. Then the same current flows by the PMOS current mirror. Then, the VGS of this thing should be the same, right? So what was that? IR drop equal VT log 4, right? NVT log 4, is it right? NVT log 4. Okay. So what's my GM? GM of this transistor is actually I over NVT. Okay. So yeah, I over NVT here is log 4. Log 4. Log 4 over R. Oh, very similar to 1 over R, right? It may be around 1.6, I'm not sure, around, this may be 1.6, not 2, right? Over R. So both, all the transistors are connected to here, yeah, each GM is 1 over R, right? Yeah, still, transistor over this GM is, GM should be W over L2, W over L times that thing. Is it right? Okay, so it's proportional to 1 over R, all right? Say, if you look at the previous netlist, so here for the strong inversion, the resistance is 810K to generate 100 nanoamp current. So all the GM of the transistor connected to strong inversion is proportional to 1 over 810K, right? And W over ratios, okay? W over that transistor, and then W over here. What's the W over? 1 by 10. 1 by 10. Okay, it compare the, okay. And then for the weak inversion, that's correct. So for the weak inversion, we use the resistor of 230K. So all the GM of weak inversion transistor is, say W over L ratio, and over, what's the W over L here? 2 by 0.7 times 1 over R, which is 340K log 4, something like that, right? So, the GM with a weak inversion bias will be larger than GM with a strong inversion bias, right? Yeah, one thing to note is that this equation is correct in the surface threshold region, but in between, in a weak inversion, it has something. It may not be exactly accurate, because there is some mixed up behavior in a moderate region. Okay, so that's why we avoid 1 by 0.7. We move to 2 by 0.7 to make this transistor deeper in surface threshold. Question?
그런 비슷한 이해가
This is a little bit, yeah, the region of used to be 360K, moved to 230K. Somehow I couldn't make it. Yeah, you may be right. Yeah, you may be right. So it used to be, we used to very, very large transistor, 10 by 0.7, right? Instead of 2 by 0.7 in the previous version. This is a very deep subthreshold at the same current of 100 nanoamp. Question?
지금 아무랑 좀 다른 얘기를 했는데 R로 그 스탠드에서 R로 값은 서브스레셜드에서 식이 나오나
Subthreshold region. Okay, the question is what's the RO equation for the subthreshold region? You know, small signal output resistance, right? In weak inversion. Yeah, we are using the same thing. So we assuming the current equation is about the same. I mean, it's something like a mu Cox W of L of gamma, yeah, gamma Vt square to square root 2 pi f minus Vbs times exponential Vgs minus Vth nVt times 1 minus exponential minus Vds of Vt. Yeah, instead of this one, we just replace it 1 plus lambda Vds, okay? In a hand analysis. So, yeah, so then we can get this small RO equation, okay? Yeah. Okay, any other question? Nope. Okay, let's move on. So then we have a bias circuit, both strong inversion and weak inversion. Let's see.